In this video, we'll take a problem from section 12.1 and take a look at two different ways to solve a proportion problem. So the problem is, according to a census company, 10.1% of all babies born are of low birth weight. An obstetrician wanted to know whether mothers between the ages of 35 and 39 years give birth to a higher percentage of low birth weight babies. She randomly selects 240 births for which the mother was 35 to 39 years old and found 28 low birth weight babies. Complete parts A through C below. So part A is taking A and B are taking a look at solving this problem using ideas from section 12.1, which is a goodness of fit test. So if the proportion of low birth weight babies for mothers in this age group is 0.101, compute the expected number of low birth weight births, 35 to 39-year-old mothers. Then what is the expected number of births to mothers 35 to 39 years old that are not low birth weight? So we take 0.101 times our sample size n, which is 240, and end up with 24.24. So that's the expected number of low birth weight births if it follows the counts above. The expected number of births to mothers 35 to 39 that are not low birth weight, you take 240 minus 24.24. So to use the goodness of fit test, you have observed values and you have expected values. So we just calculated the expected values. The observed values are given in the problem. So observed low birth weight, from the 240, there were 28 low birth weight. And then 240 minus 28, which is 212 that were not. The expected value was 24.24 and 215.76. So the null and alternative hypotheses, the null hypothesis is that the 35 to 39-year-olds follow the regular distribution of birth weights, which was 0.101. So the P equals 0.101. The alternative is we're trying to see if there is a higher incidence of low birth weight in mothers that are 35 to 39. So P is greater than. So the p-value in this case, we run a goodness of fit test. So I'm going to go ahead, use whatever technology you want to. If we use StatCrunch, I've got typed in the observed and the expected counts. Use stat, goodness of fit, chi-squared. The observed column, select observed. Expected, select expected, and click on compute. And what you'll get is a chi-squared statistic and a p-value of 0.4206. If you use the calculator, type your observed and expected into the lists. Then when you go to Stat, Tests, select Goodness of Fit, chi-squared goodness of fit. Observed is in list 1, expected in list 2. Degrees of freedom is 1. It's the number of rows minus 1. And we get a p-value of 0.421. So it doesn't matter which technology you use, you'll still get the same p-value. So the p-value is 0.421. So that means fail to reject the null. So we would not fail to reject the null. There is not evidence to conclude that mothers between the ages of 35 and 39 give birth to a higher percentage of low birth weight babies. So this question can also be answered using a one proportion z-test that we did back in chapter 10. And that's what the next part C is asking you to do, is run the question, the same question, but use a one prop z-test instead. So what we would do if it's a one proportion z-test, then we would type in, if we were using StatCrunch, stat, we're doing proportion statistics, one sample with a summary. The number of successes is 28. 28 low birth out of 240 observations. And then our hypothesis test is P is equal to 0.101. And we would have greater than, because we think there's a higher proportion, and then click on compute. And what you'll end up with is a p-value of 0.21. It's exactly half of the p-value. You could also run this on the calculator. Use tests, your 1-prop-z test. Type in the same information, 28, 240. Oops, the null hypothesis used different order here, 0.101, 28 out of 240. It is greater than, calculate. You get the same output, 0.21 is your p-value. Okay. So what does that mean? That also supports fail to reject the null hypothesis. There's still not evidence to conclude. So you can run that same question using the two different tests. The reason why the p-values are different is when you run a 1-proportion z test, we're running a one-tailed test, greater than. So it gives you on the z-score, your test statistic, or your test statistic is here, and then your p-value is 0.21 because it's a one-tailed test. But when you're doing a chi-squared test, you're looking at the difference between the two. It's generally not a greater than or less than. The alternative hypothesis for a chi-squared is different. So what you're finding, the area on the chi-squared for different, your chi-squared statistic is here, and we get an area of 0.421. If we were testing different using the 1-proportion z test, we would have both tails, and it would be exactly double. So part of it is when you run a goodness of fit, it's different. When you run a z test or a 1-proportion z, you get to have a greater than or a less than in addition to a different.